Hello, honors physics students. Okay, so now that we've learned how to do ray diagrams for lenses, we're going to do pretty much the same thing we had done for mirrors, where we're going to look at the problems, look at the math, make our predictions, then do the ray diagram and see how it all correlates. You should have already done all the math, the problems 4, 5, and 6, and made your predictions. If there's any part of that you haven't done yet, finish it up now before we start doing the ray diagrams. Okay, so for problem 4, we agreed on these numbers as measurements. Here should be the correct answers for the math. We're getting an image distance of positive 4.7 centimeters. Remember, we really want to put the positive and negative signs on all these numbers, even though they're not vectors. We know the signs will give us information when we line it up with the sign conventions. Magnification is negative 0.67, image height is negative 1.3. We know these are all 2 sig fig problems, right? You did 2 sig figs, not 3 sig figs, right? Because we measured everything only to 2 sig figs. You cannot have a third sig fig if you measured everything to 2 sig figs. We know that, so make corrections now if you need to. Okay. How did you predict the image should appear? Well, hopefully you predicted inverted, reduced, and real. We have a positive image distance, which means it's supposed to be an inverted image. Inverted images always go with real images. We see our magnification number, absolute value is less than 1, so we were looking for a reduced image. We also got a negative magnification, which also tells us inverted and real, and a negative image height, which tells us inverted and real. So all these correlate. Definitely we should be getting inverted, reduced, and real. So based on the fact that we have a positive image distance, where are we expecting this image to appear? On the left side or on the right side? You think about that. Okay, so now that we have all that done, let's draw our ray diagram. First thing you want to do is draw that dashed line down the middle. Sometimes ray diagrams will have this dashed line drawn for you. Lots of times it won't, so it's up to you to do that. Basically just connecting the ends of the lens right through that tick mark on the principal axis, and just like we did before, extend it above and below because you're not aware just yet of how much of that you're going to need. And while we don't have to go in particular order, let's go ahead and go in the same order we just did before. We'll start with our parallel ray, which starts from the tip of the object, and it goes halfway through the lens. Remember, in reality, it refracts over here, but we're going to make this approximation that only refracts once. So we extend it halfway, so that dashed line just drew. The parallel ray refracts through the focal point. So we go right here for the focal point on the other side. We don't know how much of this ray we're going to need, so draw a nice long refracted ray. Make sure you're putting arrows on both of your rays. Next we'll go for the central. The central is the easiest. All you have to do is make sure you go from the tip of the arrow right through the center of the lens. You can't go for the left side, can't go for the right side. Even think about how wide your writing device is, and go right here where the principal axis intersects the dashed line you drew, and then you just keep going. We love the central ray. It's really, really easy. Just put your ruler down and just keep going. Make sure we got an arrow on the ray though. Now at this point we have these rays connecting, which means we could be done. We don't have to draw a third one if we don't want to, but since this is our first real ray diagram, go ahead and draw the focal ray. Remember, that's when we start from the tip of the object. We go through the focal point until you reach the dashed line. And now how does this come out? It's going to come out parallel. And if you've done yours well, all three should intersect. Mine's off by just a little bit. It's a little bit tough to draw here on PowerPoint, but you know what? Hopefully yours intersected. If they didn't, well, just go with the two that you like the best. Go ahead and draw your image, because you know a ray diagram is not complete until the image is drawn. That's the whole point of the ray diagram. And then we label it, where the image goes from the principal axis to the intersection point. Alright, now let's see how this correlates. We predict it to be inverted. Is it inverted? You bet. It is pointing up, it is pointing down. Is it reduced? Yeah, you can even measure if you'd like to. This certainly is a larger, this is a smaller image. And is it real? Well, if we were to put a screen here, would those light rays actually go onto the screen? Yes, they would. Of course, also remember that real and inverted always go together for a single optical device. And so, just like we did with mirrors, we always do the math first. You can even measure, right? Go ahead and measure the size of your image. When I did it, I got 1.4 centimeters. You predicted 1.3 centimeters. So you know what? You should be really, really close to that. What about the image distance? Is it 4.7? Measure from the center of the lens over where the image is. When I did it, I got 4.7. See if you get the same. And the whole point is, right, you can do the math first. You can actually plot out where the image is going to be, how tall it's going to be, and then sort of make the ray diagram happen around it, just in case you're not really good at ray diagrams. Let's go on to problem 5. Now again, we've got a converging lens. It's convex in shape, thicker in the middle, thinner on the edge. Here's our math answers. We'll be getting negative 28 centimeters for image distance, a positive 2.00 for magnification, and positive 3.8 centimeters for image height, where again, we measured this in 2 sig figs. We only have 2 sig figs in our height, but these were given as 3 sig fig numbers, so we're allowed to use 3 sig figs in our answer. Let's look at our image prediction. Hopefully you predicted upright, magnified, and virtual. We have a negative image distance, which goes along with upright and virtual. We have a magnification larger than 1 that's magnified. Magnification is positive. Image height is positive. All these correlate to upright, magnified, and virtual. So where are we expecting this image to appear? Think about that for a second. All right, let's see if it happens. So let's go ahead and do our ray diagram, starting with our dashed line down the middle. And go ahead and do some rays, then come back to the video to see how I did it. Here I've drawn the parallel ray going through the focal point on the other side. I've drawn the central ray because it's easy, just goes right through the center of the lens. As we've done with mirrors, when this object was within the focal length, drawing the focal ray is rather tough, because if we start from the tip of the arrow and go this way through the focal point, what's going to happen is we're going to miss the lens, which means that's not the way to do it. Now, there is a way to do it, but we'll go through that in a little bit. Regardless, it doesn't matter. Remember, as I've been saying, we only need two rays to interact with the optical device, in this case to refract and go through the other side, and wherever they meet is where the image appears. But what are these rays doing? They're not meeting, they're spreading apart. So how are we going to find where the image is? Well, remember, when it comes to light, humans are stupid. That's right. So let's imagine you're over here, the lens is in your hand, and you're looking at some object through the lens, the object's on the other side, and these light rays are coming towards your eye, and we think that light comes to us in straight lines, and so your brain naturally traces them backwards. That's right. So we're going to trace the refracted rays backwards. This ray traced backwards, this refracted ray traced backwards. They will certainly meet on the left-hand side. Make sure we are tracing the refracted rays backwards. Make sure we're using dashed lines because they're imaginary. And remember, there's no arrows on these traced back rays because the light doesn't actually go this way. We just think it's coming from there. And wherever they meet, that's where the image appears. And so here's our image drawn from the principal axis to the connection point. Let's see if it correlates to our prediction. Is it upright? You bet. Magnified? Oh yeah. Virtual? Let's think about this. If this is a source of light, like a candle or a light bulb or something like that, I put a screen over here, will light from this go onto that screen? Well, yes. Of course it will, right? If there's a candle or a source of light, light goes in every possible direction. We're just looking at some of these light rays that go through the lens, but some of these light rays will definitely go onto the screen. So, doesn't that make it real? Well, wait a second. Let's think about this. Look at the light rays that go from the tip of the object to the screen. What have they not done before they got to the screen that these light rays did? Oh, they didn't go through the lens. Remember, the whole point of this whole topic is using optical devices to manipulate light to form images. If there's a light ray that goes to the screen but never goes to the optical device, well then who cares? Why even bother having the lens? We need to look at light rays that go through the lens, and then we trace back and see if they connect. Now, if you put a screen here, would this light ray go through the lens and then back onto the screen? Well, no. That doesn't make any sense. And so the light rays that got refracted, they're the ones that do not go onto the screen. That's what makes it a virtual image. Of course, we also know virtual goes with upright, and we trace light rays backwards, making it virtual, but I want to make sure we're very clear about what it means for light to go onto a screen. We only care about light rays that interact with the optical device and then go onto the screen to make a real image. Since they don't do that, it is a virtual image. Does that mean you can't see it? No, absolutely, you can see it. You absolutely can see a virtual image, just like we saw with the mirrors, just you can't get it onto a screen. Okay, now there is a way to do the focal ray. You might recall when we did this for the converging mirror, we imagine a light ray that starts here at the focal point and goes this way up to the tip of the arrow. Now you might remember we did it for mirrors, it didn't work very well, but for lenses usually it does work pretty well. So here's the idea. Use your straight edge and connect as if you were going from the focal point this way, and start from the tip of the arrow going up towards the lens. You're probably going to have to use your extended dashed line. We know the focal ray comes out parallel. Remember, it's still going to the right because it's going through the other side. It comes out parallel, but then when you trace it backwards, that's where it should connect with the other two. As this one, most students have a lot of success with. But remember, all you need are two anyway. You don't need a third one. It's a good check. But most students have success with this. But just as I mentioned with the mirrors, make sure we're not just drawing this ray and then tracing it backwards. Make sure we're drawing the refracted ray as well. The incident ray, the refracted ray, and then if you need it, draw the dashed line backwards to see if it connects. Let's look at our numbers. We predicted the image distance to be negative 28 centimeters. The focal length was 28 centimeters. So this object appears right here. The image, I should say, appears right here on the focal length. So that if you got to be right there on F, you did a really good job. You can even measure if you'd like to. We should be getting a height here of 3.8 centimeters. When I measured mine, I got 3.7 centimeters. You should be really, really close, which is why we always do the math first, then look at the ray diagram. Let's try number 6. Alright, so here's what we got here. You should be getting negative 0.786 centimeters, positive 0.286, positive 0.54. You notice that this is a diverging lens. The problem even told you the focal length is negative, but even if they hadn't, we know that all diverging devices have negative focal lengths. That's your job to put negative focal length in for the math. Let's look at our predictions. We should be getting upright, reduced, and virtual. Hopefully you got all those. And negative image distance is virtual. Virtual goes with upright. Magnification is less than 1. And of course all the other signs correlate as well. Alright, let's draw our dashed line down the center. Go ahead and start doing your parallel ray. Just do the parallel ray, then come back to the video. Okay, so here's our parallel ray. We know it starts from the tip of the object and then goes halfway through the lens to our dashed line. And then what did you do next? Remember, this is a diverging lens. This is a diverging lens. This is a diverging lens. If you have this light ray going through the focal point, that's not right. That's what a converging lens would do. Get rid of that, right? Why would we be doing the exact same thing? This is a diverging lens, which means when it goes through this lens, where's it going to go next? Yes, of course we know it's going to go to the right, but it's going to go to the right and up. And not just to the right and up at any random angle. We saw this before when I showed you the picture. Parallel rays of light that go through a diverging lens diverge as if they came from the focal point. So we have it go up and to the right, and make sure you connect back to the focal point using a dashed line. This light ray, if it were to trace backwards, would connect to the focal point on this side. This is the wrong side of the lens. This is a negative focal point, or the virtual focal point, if you want to think of it like that. How about the central ray? Well, the center of a diverging lens is sort of like that rectangle, so there's really no difference here. It's going to go straight through. Go ahead and do that. Nice and simple. We don't have to worry about it. And we're going to do the focal ray, but it's a little more complicated. But it doesn't matter. As long as we have two rays to intersect, they don't intersect because it's a diverging lens, which makes sense. So what do? We trace it backwards. Luckily, this one's already traced backwards. And you know what? It is traced backwards too because it's all in one straight line. So right here is where the image forms. From the principal axis towards that connection point, we label as image. We're good. Let's look at our predictions. Is it upright? Of course it is. Is it reduced? You bet. Is it virtual? Well, we did have to trace the light rays backwards, certainly. We know upright goes to virtual, but more importantly, what if we put a screen here? So there's a source of light. If I were to put a screen here, would I get an image onto the screen? Well, first, would I get any light on the screen? Yes, of course, right? Some of these light rays will certainly go onto that screen, but again, they haven't gone through the lens. In fact, if I put a screen here, I'm actually blocking light from ever going through the lens. There's no way you're going to get a focused image onto this screen. That's how we know it's virtual. Alright, so what about that focal ray? Well, you may already know what to do. Considering this is a diverging lens, it does the same sort of things as diverging mirrors, so what do? Well, we start from the tip of the object and we draw it as if we're going to go towards F on the other side. When we do diverging devices, we're always using the wrong focal point, or the opposite focal point compared to what we do for converging devices. So let's try this. Start from the tip of the object, head towards the focal point on the other side, but remember, we've got to stop at the dashed line. What happens when it gets to the dashed line? It's going to refract. We know it's going to refract parallel to the principal axis. As it's diverging, we spread it, spread apart, we trace it backwards, and it should intersect the other two. We'll be really, really close. In the end, though, remember, you only need two of these rays, and as long as you find where they connect either on the other side or trace them backwards to this side, we've located the image. Now recall, for diverging mirrors, we talked about what happens when we move the object. So anywhere we move this object, we know that these rays will diverge. If they diverge, we'll trace them backwards. Tracing backwards makes it virtual. Virtual is always upright, and by the geometry, it's always going to be reduced, and so diverging lenses, just like diverging mirrors, only do one thing. They only make upright, reduced, and virtual images.